So there's 10 questions on the test. 5 problems are based on the curve sketching problems. 2 are limits that are based on the Hopke-Cult rule, and then there's 4 that are word problems. The test will be basically the same, just different numbers, but will be basically the same design. So we want to find the minimum and maximum values for this function. So to find my minimum and maximum values, what do I need to figure out first? I need the derivative to find my critical numbers. So y prime So how do I find my critical numbers? Set that equal to 0. So 8x to the third equals 8. X to the third equals 1. Third root. X equals 1. So I've got my critical number. So plug it back in, we can find the value for the original problem. So my point is going to be at 1, -6. The question is it a minimum or a maximum? How can we determine that? Yeah, we can take the second derivative of it. And that'll tell me at that point if it's negative or positive. That'll give me that value. Can we do it with the first derivative so I don't have to take the second derivative? You could just look on either side of it, of that critical number, to see if it's going to be positive or negative. So if I just plug in 1, I can plug in 0 and 2 and see what happens to the problem. If I plug in 0, I'm going to get a negative. And if I plug in 2, it's going to be positive. So it's decreasing into it, increasing out of it. So I know that's a minimum. If I did find the second derivative, we end up getting 24x squared. So at 1, that would be positive, so it's concave up, which means it's also a minimum. So for this question, you have to tell me the point and is it a minimum or a maximum? So you have to show me some way that you calculated to determine what it is. You can, but you can't say I graphed it on Desmos. Yeah, you have to show me why you know it. So actually, this is one of the really good reasons to actually know this stuff out with not necessarily using Desmos. So here's what the graph looks like. A fourth degree equation has a tendency to do other loops and stuff in there. I don't know if this one actually does. I think this one actually just goes like that. But that's the question. It's like when you're looking at this point here, it's like, okay, that might be a minimum, but I don't know what's happening outside of this window that I'm looking at. It could come back down at some other point. I don't know. So that's where you're looking at, like, we have to do that graph. But now that I know my critical numbers, there's only one critical number. I know that is the only point on this graph that it is going to do that drop. So you can use Desmos to verify knowing, okay, this is going to be a minimum because of what I'm looking at here, but you still need to be able to show it algebraically as well. All right. Any questions on that one? Keep getting wrong this week. Hey, next one. All right. So, are there any domain restrictions for this problem? Right. So this inside the square root can't be greater, or has to be greater than or equal to 0. So x squared plus 2x has to be greater than or equal to 0. Or we go the other direction and say less. So do not move the 2x over and do it that way. Factor. So we have 0 and -2. But those are the equals. We need to figure out where on the continuum it actually works. So if I plug in -5, -1, and 1. -5, I'm going to get a positive. -1, I'm going to get a negative. And 1, I'll get a positive. So I probably should change this to say find the domain and not restrictions, but so it's -infinity to -2. And then 0 to infinity. All right. So now we have to figure out if they're the asymptotes. So are there any vertical asymptotes in this one? So this is one of those situations where there's a restriction, but there's not a vertical asymptote. Because it equals that there's a point that equals at -2 and 0. It's not going to infinity. It's literally stopping at that point. So there is no vertical asymptotes in this problem. Is there any horizontal asymptotes in this problem? So for a horizontal asymptote, we need to look at the limit. So as x goes to infinity, do that side first. All right. What's the limit as it goes to infinity for this one? If you plug in infinity, what do you get? Infinity minus infinity. Is that a valid? So it would be 0 in that respect. But is that valid? Infinity minus infinity is one of the I can't think of the word right now. Yeah, it's one of those things. So what do I got to do? Okay. The question is, how do I do that? Yeah. So we're going to have to do, so I would do the conjugate first, because the way it's set up right now, I can't do L'Hopital's rule, because I don't have a numerator and a denominator. To do L'Hopital's rule, I need that. So no matter what we do, we're going to have to do the conjugate pairs to get it to do something. So let's look at a conjugate pair for this one. I'm going to multiply the top and the bottom by the square root of x squared plus 2x plus x. Same thing on the bottom. So this becomes x squared plus 2x minus x squared over so I've got 2x. Okay. What am I doing now? Can I do it? So I have this limit now. We could. You could do L'Hopital's rule with this one. But there's actually kind of an easier way. Actually, you know what? Yeah, let's just do L'Hopital's rule. The other way too. Yeah. So we'll do L'Hopital's. This is infinity over infinity, so L'Hopital's rule will work. And I can't just plug in infinity to it because I'm going to get infinity over infinity. So what's the derivative of 2x? 2. So now we got to find the derivative of the bottom. So it being 2x plus 2 times 1/2. So we've got so I don't think that helped us. Yeah, I don't think that helped us. Because you still have infinity over infinity here. So yeah, let's try the other way. So we're going to go through, we divide by the highest exponent in the denominator. So which in this case is x. So we divide the top by x and everything on the bottom by x. So this ends up, top ends up going to 2. The square root ends up being x squared over x squared plus 2x over x squared. So that is the square root of 1 plus 2 over x plus 1. 2 over 2, which is 1. I'm not done. Of what? What negative 1? What do you mean? Oh, when you do the square root? Oh, sorry. I am done with that part. If the square root's already there, you include, it's based on whatever sign's in front of it. When you're taking the square root of something, you have to take the plus or minus because you're actually looking at the square of it and not necessarily the square root of it. That makes sense? So if I have x squared equals 16, I'm not looking for the square root of 16. I'm looking for what x squared is. That's going to give me the square root of 16, or give me the 16, which would be the plus or minus 4. If I'm saying x equals the square root of 16 is already done, I'm doing the square root of 16, which is just 4. So that's the difference in when you're looking at the plus or minus or not. Actually, what I thought you were going to talk about is that is my horizontal asymptote going to positive infinity. I still need to look at going to negative infinity. So if we look at this as x is going to negative infinity. So actually, let me just write this one. Yeah. If you plug in negative infinity, what are you going to get inside the square root? You do technically get, you do actually get negative or infinity minus infinity. I will give you that one. However, if you look, I will allow you to do this every so often. If you look at that, which one's getting there first? The x squared is going to be bigger than the 2x. So it is definitely going to get there first. So that one's infinity, and then it's going to be minus a negative infinity, which is really plus. So you have infinity plus infinity. So that goes to infinity.
Why wouldn't it be one?
What do you mean one?
Like for the last one, we did the conjugate rule and then shakes 2 over 1 over x plus 1. They plug into that be just 1, right?
If you plugged in negative infinity here,
Like, why didn't we do all that again?
because you actually have to look at, if you're doing the negative infinity, it's the square root, that's going to end up being negative. Because you're going the other direction. So you end up getting 2 over 0. Yeah.
Why were we able to not do it this time? Like that whole,
Oh, you could have done that whole process out.
yeah, but you said but like that.
Oh, for this one?
Yeah.
Because in this one, it wasn't the actual inside the square root that changed. This whole process was infinity minus infinity. It wasn't just under the square root. So the question was, is which one's going? Is this going or that one? That was a little more complicated to like mentally figure out, and it actually didn't go to infinity. Where in this case, the x squared's obviously getting there faster than the two x's. So, and then just as everything, use Desmos to verify your work. If you're looking at it, that's shooting off to infinity. And if you look at this, that's getting closer to 1. And notice how these 2 points end at those. And at 0. So we don't have a vertical asymptote in those cases. All right. Any other questions on that one? Because vertical asymptotes means it's going to infinity. It's shooting up or shooting down or going down in the same spot or whatever else. So it's getting closer and closer to that point. In this graph, it's not getting, actually, it's getting closer and closer to -2. It's not getting closer and closer to an actual line. Where this one, as you're going further and further out, it's getting closer to 1, but it's never going to reach 1. That's why that's the asymptote. So you'll typically, like, if we had the equation like 1 over x, that's a clear vertical asymptote because it's getting closer and closer to 0, but never actually going to touch it. So that would be a vertical asymptote. All right. Concave up and concave down. What do I need to find? Need to find my second derivative. Find me my second derivative. What rule do I need to use for it? Yep. So if I make f dx, f prime is 1. G prime is 2 times 1 over x ln of x. All right, so what do we got? We got ln of x squared plus x times 2 ln of x over x. So now we find our second derivative. So I have 2 ln of x over x plus 2 over x. All right, so what do we got? So to find my concave up and concave down, I need to do what from this point?
Figure out what the second derivative function is positive or negative.
Well, I need to find my critical numbers first. Wait, repeat what you just said?
Find the critical numbers, first derivative, that you plug in that number line kind of that we've been doing, second derivative. Now tell us what it's not.
You're so close. That's it. We need to find our critical numbers in the second derivative. So the first derivative, if you find the critical numbers of the first derivative and plug it into the second derivative like we did in the first problem, it will tell me the concavity at the mins and maxes. But it's not going to tell me where they're changing because those are not the same place. So when you find the critical numbers of the second derivative, that's going to tell you where it's switching or should switch from concave up to concave down.
Okay.
So. So I need to find my critical numbers for this. So how do I find my critical numbers? Set it equal to 0. So 2 ln of x, or ln of x equals -1. So how do I get rid of the ln of x, or the ln? What's the inverse of ln? E. Sorry, it's supposed to e. So x is e to the -1st, or 1 over e. Do I have another critical number in this problem? So where is it undefined? So if I have there, because remember, I can also have the denominator equal to 0, so that's equal to 0. So I have 2 critical numbers. However, only one of them is actually going to be a critical number. The 0 is not going to be a critical number because 0 is not in your original domain. Remember, your critical numbers still have to be within the domain of the original function. So in this case, my original function has an ln of x in it, and ln of x, that can't be 0.
How did you get the 0 for the other?
Oh, I just set the denominator equal to 0. Because the two critical value, the 2 places the critical numbers could exist are when the function equals 0 or when the function does not exist. And in this case, the function doesn't exist when x equals 0 because the denominator can't be 0.
Why is it that when a function doesn't exist, it's a critical number?
Because it could, that's where something can happen. Either an asymptote or,
Is that the definition?
yeah, critical numbers are where things can change. So that's why we're looking for those things. A lot of times, the only ones that really end up doing something that we're going to use is when it's 0. But you can have asymptotes and other possible things that happen at that point too. So that's why you have to look at them. So, but in this case, that was the statement. It's like when we looked at it, x is not in my original domain, therefore I don't need to actually use it in this case. So the only critical number is that. Now I need to figure out, is it concave up or concave down on those intervals? So I do my quick little number line 1 over E. I can't use 0, but I can use 1/2. And I can use 1 on the other side. So, yes.
Would 1/2 still be greater than 1 over E?
Oh, you're right. Yeah. I'm thinking, I was going, okay, E is 2 point something. So you're right. Very good. Good catch. So let's do 3. Good catch. Now, this one, honestly, I would just type it into Desmos and get the answer. I'm not doing this off by hand. Not the graphing calculator, Desmos, the actual scientific calculator to get your value. So I would literally do it like this. Type the equation in, plug in x equals 1/3, and I get a negative. And if I plug in 1, I get a positive. So since the original function can't go less than 0, I'm concave down from 0 to 1 over 1 E. And I'm concave up from 1 over E. Yeah, I'll probably take off the point for that. You can't be, so by definition, you cannot be concave up or concave down or increasing or decreasing or have a negative slope or positive slope at a specific number.
Oh, so it's always.
There are always going to be parentheses when you're looking at these intervals, yeah. So, and if even decreasing, you can't decrease at the point where you're decreasing to, those critical numbers are zeros. So technically it's not decreasing at that point, it's 0 at that point. So this is actually what the graph looks like. And that's where it switches from concave up or concave down to concave up. All right, next one. All right, increasing and decreasing. Yes, you will need to do the product rule. Do that. Hold on a second. Oh, well, that's the machine. Like, wait, something was off. There we go. These are the ones that, unfortunately, while you're doing them, you kind of need to simplify them down to do the next step. So you kind of want to simplify it as much as possible and get it organized. So, I hope nobody has trouble finding the derivative. We'll go with that direction. However, going to the next step, I had to find a common denominator, so I multiplied the second part by the 3 square root of x to the 1/3, which gave me just 3x. Because x to the 2/3 plus or times x to the 1/3 is x to the first. And then I just distributed the 2 through to clean it up a little bit more. So, where are my critical numbers? And this one's going to actually have the thing with the critical number where it doesn't exist. What are my critical numbers for this one? So we have 5x minus 12 equals 0. So x equals 12/5. And x equals 0, so x equals 0. I don't have any domain restrictions in the original problem. So therefore, both of those values are ones that we need to look at.
How did you simplify the first derivative you got into the 5x minus 12 here? 3, 2.
X to the 1/2, 1/3, X to the 3rd, so it gives you X, just X. Okay.
Get that, oh, okay. I see.
Yeah, and then I just distributed it. So we've got 0 and 12/5. So -1, 1, and 3. So plug in those 3 numbers. -1 gives you a positive. One gives you a negative. And 3 gives you a positive. So in this situation, that 0 actually does change direction. So I have increasing from -infinity to 0, and from 12/5 to infinity, and decreasing from 0 to 12/5. So if we look at this one, this is what the graph looks like. The black, that's the actual graph, and that's the derivative. So there is something happening at where the derivative doesn't exist. So it's one of those situations where it does actually come up. Any other questions with that one? All right. Points of inflection. Where are my points of inflection?
Points to the second derivative.
Critical points of your second derivative. So find my second derivative. All right, so we've got x equals 1 as my critical number. Is that what it's asking for? So yes, we found our critical number, but it wants the point of inflection. It wants the y value too. It wants the actual point where it's inflected. So you have to take your critical number and plug it back into the original problem to find where that point actually is. So the point is at 1, -11. And if we look at the graph, it's going to switch right around there. And that makes sense. All right. Any other questions on that one? All right. Find me the limit. You plug in pi over 4, what do you get?
0/0.
You get 0/0. Don't forget to plug that in. Don't forget to try to plug the numbers in. There is always a chance I'm going to put a problem on there that that's all you need to do. I did it on the first test. So there's a possibility that that will show up again. So don't do that. Or at least try to plug it in first. This one does come out to be 0 over 0. Since it's 0 over 0 and it is a fraction, I can do L'Hopital's rule. So let's do L'Hopital's rule. So what's the derivative of the top? And the derivative of tangent of x. And one's gone. All right. So now if I put in pi over 4, what do I get? So sine of pi over 4 is square root of 2 over 2. Cosine of pi over 4 is square root of 2 over 2. And secant of pi over 4 is square root of 2. So I get negative square root of 2 over 2. You will not be able to plug this into Desmos to get the answer. It will give it to you as a decimal, and I do not want a decimal. Yes.
Square root of 2, that's square.
Yes. Yep. Yeah, because I just over here, these were just the straight functions, and I had the square. Then I plugged it back in. Yeah. That's fun. Plug in 1. What do you get? We get 0 over 0. But, and this is why, a simple change to that is now 1 over 0. So that would be infinity. So that's what I'm saying. A quick little change, even if it's problem does, and that's all I'm making on the actual final test is little changes. So always try first. So find my derivative. Alright. Now on to the fun ones. That'll be nice. I'll give you a picture. All right. So what are the equations that I'm going to have for this one?
Area is equal to x times y.
Yeah. So the area, we're going to keep it in terms of x, will be x times y.
Why do we keep it in terms of x?
You could have done it in terms of y, I just chose x. It doesn't make a difference which one you choose. All right. What's my other equation going to be? The more complicated equation. What's the only number they give you two numbers. Both numbers are in relation to what? Price. So my other equation, a lot of times when you're doing these, the other equation is going to be in terms of perimeter. And this one, it's going to be in terms of cost. So the cost equals what?
And y plus
So that's the 10.
15x because it's going to be 2x.
Right. So this one will be 10,
And then that one's going to be half that.
and that'll be half that. So it's 10 times 1/2 x, which is 5. So plus 10x plus 5x. And the cost actually equals, well, it's got to be less than or equal to 7,000, but we can set it equal to 7,000. He's going to willing to spend that much, and we're going to max out the area, so we max out the price. So we're looking, so right there, those are going to be your, that's the length, right? So, but I don't want the length, I want the cost. So this side is going to be 10 times whatever y is. That side right there will be 10x, because that's that side. And since this side is going to be half x, I multiply that by the 10 as well.
Yes. Why is that?
Because the farmer on that side is willing to split the cost. So he's only paying for half that fence. So my farmer is only paying $5 a square for a linear foot on that side when I'm calculating it out. That's honestly, when you're looking at these, those are the little catches that like, because that's going to change the answer. So now I'm going to want to solve this one for y. Rewrite that one in a minute. So 10y plus 15x equals 7,000. So 10y equals 7,000 minus 15x. So y equals 700 minus 1.5x. I'll do it as a decimal. All right, so now we're looking for the maximum, right? So we're looking for the most area, so the maximum. So how do I find the maximum value? So find my derivative, find the critical points. So we can change this into a decimal. Because when we're doing these anyway, he's not buying. He's not going to go to NASCOM Depot for 700 divided by 3 feet. So we can change it to a decimal. So x equals 233.33. I still need to find y, because that's the x dimension, but I still need to find my y dimension. So y will equal 700 minus 1.5x. So the y is 350 feet. And those are my answers. Yes, technically you should find the second derivative to figure out if it's a minimum or a maximum, but I'll give that one to you because it's obviously going to be a maximum, not a minimum at that point.
Because we said it, you really said. the
Yeah.
maximum.
Yeah, we said it's the maximum amount of money he's going to spend. So, and there's only one critical number. So, all right. This is a question you will only probably see in the Northeast. Well, in older places with older houses, because we have a lot of these windows. All right, so if the perimeter of the window is 8 feet. So there's a few little things that we can do to modify this picture a little bit easier so we can understand it mathematically. So we have a rectangle and then a semicircle. So the perimeter is going to equal what? Correct. 8. Okay. But now how do I find the 8?
What is the height of the rectangle under the semicircle?
That'd be area.
And x plus half of the circumference.
Yep.
Given the radius of 1/2 x.
Yes. Okay. So we've got x plus 2y for my rectangle, correct? What's the circumference of a circle? Yep, 2 pi r. So it's 2 pi times x over 2. And I only want half that. Because that'd be the whole circle. And I only want half of it. So we can clean this up a little bit. X plus 2y plus x pi over 2. Why?
Because for adding it'll to get the perimeter of the semicircle, the dotted line wouldn't be included in it.
Correct.
So what it would just be 2y plus x pi over 2.
You forgot the buff.
Well, that is the bottom, but after you subtract, so you have x plus 2y's semicircle.
So that's the x. That's the 2 y's. And that's the semicircle.
But the perimeter we use the equation to find that for x pi over 2 would include the dotted line.
No. Because it would be, so the 2 pi x over 2 is the whole circle. By dividing it by 2, I'm cutting off the bottom of the circle, not including that line. I'm just cutting off the bottom of the circle. All right, so I've got to solve this for let's solve it for y. So I have 2y equals 8 minus pi over 2 plus 1 x. So y equals 4 minus pi over 2 plus 1 divided by 2x. So just messy, but it's still just a number. All right, so now I need to find what? I want to maximize the amount of light. So what am I really looking for?
The area.
The area. All right, so the area of this is x times y plus, what's the area of a circle? Pi r squared, and I'm only on half of it, so divided by 2. But r is inheritance. X over 2 squared. So a of x equals x times 4 minus this whole big huge mess here that I probably should just get into the decimal right now. Since it's a real life problem, I can do that. Because I'm tired of writing it out. $1.29. So we've got 4x minus 1.29 x squared plus pi over 8 x squared. $1.68. Negative 0.89. All right. So now what do we do? Find the derivative.
And set it to 0.
Set it to 0. We've got 4 divided by 1.7. 2.25. We plug it back in here. You get y equals 1.10. if you did it exactly without actually rounding or anything else, it actually comes out, the y comes out to be exactly half of what x is. If we didn't estimate any of the values at all, it would have been exactly 1/2. And if you think about it, if y is exactly 1/2 of x, what's the actual height of the window? The height of the window is exactly x, because that's half of x and that's half of x, which would be this is just like a square, which would be optimizing your area. All right, the last problem of this. All right, how are we going to go about doing this one? So a fence runs 8 feet or 8 feet tall, runs parallel to a tall building with at a distance of 4 feet from the building. What's the height? What's the length in feet of the shortest ladder that will reach from the ground over the fence to the wall of the building?
Define L matrices.
Okay. So we don't have enough information as it sits to figure it out the whole length. So we're going to have to do this as 2 separate pieces, right? Because I don't know that. And I don't know that. So we don't know this or this. So I could find that length. So what's that length? So what's that one? So that's the hypotenuse, right? And I have my what? Opposite. So which one's opposite in hypotenuse? Sine. So I have sine is, or sine of theta is 8 over h. And if I need h by itself, that becomes h equals 8 over sine of theta, which is going to be easier just to write as a cosecant theta. So I have 8 cosecant theta. So then what's that piece? Was it? Cosine. So cosine of theta is 4 over h, right? So h equals 4 over cosine of theta, which would be 4 secant theta. All right.
Alex. Let's do with the jet bug too.
How did it show it?
Which is more step.
Yeah, it just depends on like. So this is one of those ones you can do it either way. I like this one. So the other way that it actually shows you actually do it this way. Which is just minimize, which is your similar triangles to minimize it down. This one works, but you have to use implicit differentiation to solve it for it. So it's a little extra work. This one looks easier. The problem is we still need to find the derivative of this. So you kind of got to remember your derivatives for these, and that's where that comes into play. I have noticed, so me and Malcolmstein are probably not going to recommend them using Alex for calculus next semester, just because of honestly, until they fix the explanation issue. That's the biggest problem in there right now. Like when you get the answer wrong, it should show you why you got the answer wrong, and it doesn't do that. But in terms of my chatbot, if you actually like say, "Hey, can I use this with trig?" it would have actually changed it because I actually played with that the other day. So you can actually ask it to do other methods, which is kind of nice. All right, so how do we do this one? I need to find the derivative of it, right? So what is the derivative of this? What is the derivative of cosecant? Yeah. So it's going to be 8 cosecant theta cotangent theta. And then secant is secant tangent.
You have to memorize the derivatives of the secants.
You get your index card. All right. So now what do we do?
Right up with three functions in terms of sine theta and cosine theta.
We can, but what do I got to do before I even get to that point? I got to set it equal to 0. So if I set this equal to 0, we can, I'm actually going to move one over. So we get 8 cosecant theta cotangent theta equals 4 secant theta tangent theta. Oh yeah, it would be. I know there's something in there. All right.
It will be positive because
Did I miss?
negative cosecant.
Oh, you're right. So actually, they would have moved to the positive. I missed that negative. Okay. All right. So now probably changing them over would kind of help, or when I move things over, kind of change it. So like, if I divide both sides by cotangent of x, or cotangent of theta, that's really the same thing as saying 8 cosecant theta equals 4. Let me divide it by, yeah, I'll go to the direction for that one. Secant theta tangent squared theta. And if I do the cosecant theta, just right, get rid of that. What's secant theta over cosecant theta? Secant is cotangent. So cosecant is secant. So that's really, or sine. So it's really sine over cosine, which is tangent. So I have tangent to the third theta. So tangent theta equals the third root of 2. So theta equals the arctan of the third root of 2. So now they wanted what? They wanted the length of the ladder. So I now have to put in the theta into here. This is another great use case for Desmos. So X is that. And then I'm just going to type in 8. I don't know if it'll do. That's right. Fine. That's plus, right? 4 secant. So you don't have to type that in. Because otherwise you'd have to type that in for both of the X's. So the shortest length of the ladder is 16.6 feet. Yeah. Oh, it actually says rounded 2 decimal places. I missed that part. Fine, 6.5. That's what I get for copying a book for problems in the book. That's your test. Remember, no class next Tuesday? Your test is next Thursday. You have until Thursday night to finish up the chapter 4 stuff, but on Saturday everything opens up again anyway. Next Saturday. Any questions? Yep. I'm just changing numbers.
No business ones.
Nope.